Welcome to a new test and teardown video. This time we're going to look at another oscilloscope from Philips. This one is called PM3295. And it is 350 megahertz analog oscilloscope, 2 channels. We got a little bit of a digital assist and a little bit of digital readout, but it's not really that much digital. It's almost 14 kilos heavy and 52 centimeters deep. It's using 130 watts. So I think you can hear the fan. There's a little bit of funny things with this scope. You see, we got digital readout here inside the screen. And it's blinking a lot. It's about the refresh rate. I think that has something to do with the shutter time of my camera. And then we got those 5 LCD readouts, and they're saying exactly the same as what the screen is saying here. So what is the point? Here's 500 millivolts per division. Yeah, but you got the same information here. So what is the point? See? Clickety, clackety, clickety, the same information. And of course it says on cal here. And it just say less than. I mean, what's the point? I don't get that. I just don't get it. But there's another really cool thing about this scope, and that is the auto set. Clickety, clickety, click, and then we're happy again. It goes through all the different settings to optimize the readout. And then you have to turn off channel B because it turns on both of the channels. And it's very bright. And that will be the readout intensity. And that will be focus. Yeah, so that is the first impression. Those really funny things. And we got, of course, dual time base, delay time base, and there's a lot of delta thingy, funny stuff going on here. I'm still playing a little bit with the delay time base, and here we go. That's our 2 time bases running, and here you can, of course, select your delay time base. How fast is that? And all that, and here is the view, and this is the master time base again. But the fun thing is, it's not responding to delay time base here. I've been trying to click on all those different things here, and I can't really figure out how to make it. Now we got finally a little bit of response. But it took me a long time to figure that out, and this is not analog. I mean, see what happens here? Absolutely nothing. And then I go the other way again, and then suddenly, click, we see some more. I don't know, let's see if that will work. Yeah. I am not super impressed about that. So there's probably some weird things going on here. And then you have this one, of course, and then... Yeah, okay. A little bit weirdo things going on here with that. And here we go with the cursors. Yes, of course we got cursors. And so that is the voltage cursors. And of course we got time cursors. I mean, really... We need to have cursors, so, and that seems to be working. So now there's a good response here. Ain't that fantastic? and it tells us how many milliseconds. Wonderful. Yes. I'm still playing with those cursors. This is going to take forever. I don't know. Please tell me if I'm an idiot, because look what I'm doing here. I enable the time cursors. That's what it says. Time. And if I hold it or do whatever I do, there's no other way to get time. Okay? So then we got 4 different options down here. One is track, and that means both of the cursors, they track. Fantastic. Then I click delta, and then I move one of them. Okay? And then I can click ref, then I move the reference. So far, so good, right? Or if I click ratio, then I get it in percent. So if I want to know something in percent, then you can do that. What the heck is that used for? But anyway, why can't I get the frequency? Hey man, what am I doing wrong here? This must be able to... There must be a way, otherwise I'm gonna murder myself. This can't be. So here's what I'm doing. This is 500 millivolts peak in 1 kilohertz. This is also the same as -2 dBm, because I'm running the signal into a 50 ohm load. Okay? And this is what I recommend to do when you're testing bandwidth on fast scopes, and they do have an internal 50 ohm. You want to use this instead of adding your own through load, because this one is sitting directly into where it needs to be, right? So let's crank up the juice. This was 1 kilohertz. Let's just go straight to 1 megahertz and then go fast. Oh, you can definitely see this is analog time base. So this is the same. Of course, this is 0% and 100%. So that was 1 megahertz. Let's dial it up to 10. And then a few more clicks here. And 10, okay, still the same, yeah. 100. And of course, still the same. So what we need to do now is we need to add a little bit of intensity. And now we have 10 nanoseconds per division, and we are in full speed, yes, of the main time base. But we have another little trick here. We can add 10 times magnifier on time base. So now we have 1 nanosecond per division. So I will probably go a little bit down here. 2 nanoseconds. This is a 100 megahertz signal, and still no detectable attenuation. So let's crank up the frequencies. 200 megahertz. I should probably fine tune, yes, the trick. And let's go to 300. And now you see the signal attenuated. I will crank it all the way up to 350, the specified level. But as you see here, the signal is about 10% and 90 as it is supposed to be for -3 dB. But we didn't... why is it not moving? Okay, it was a little bit sticky. So, we didn't account for the loss in the coax cable, and I got 1 meter of RG58. And at 350 megahertz, there's 1 dB loss in this cable. So now I'll go back to my signal level and I will crank up 1 more dB. So now it is fair to say that I still have the same level as I started with initially, right? So now we go back to the frequency and continue up to 400. And we can go on a little bit more. Here we go. 440. So I believe that is the true bandwidth of this scope. Isn't that fantastic? So now it's time to go inside and have a look. We got a few things that we need to look at. Mains power switch is disabled, removed, bypassed somehow. So the owner told me to be very careful and added some sticky tape here to tell me be careful about that. Some problem is here, so I will be very careful. This one is quite a task to open, by the way. You need to take away the rear and then pull out everything. And I look forward to play a little bit with that. Let's look a little bit on the back. This is, of course, where we need to get in here. We remove all this. We got a few screws here and here. So this is what I want to do. So this one got the IEEE bus. And this is a little bit weird. Why? This is an analog scope, right? Or am I again doing something completely wrong? Or is this only for setups and stuff? I don't get it. And I'm even more confused about this. It says memory backup battery. And then we got some batteries right here. So this really? How is that going to work? But I must say plus points for having the batteries outside, easily accessible, and a nice clear indication here what is going on. So that is great. Previous models of Philips scopes had the batteries inside and no signs of anything on the outside. You just needed to figure this out by yourself and remember to change the batteries. There was just no free space around to pull out the cover, so it's scratching all over the place. Look at that, I didn't do that. And the whole frame here just touches all the way around, so you need to pull and wriggle and fight to pull off the cover. And this thing is nearly 14 kilos, remember? So you can imagine how hard it is to pull this out when it's scrapping everywhere. It's just... So it's a two-man job, you know. Ask a friend for some help, and then you will get it out. Let's start with the top. Of course, this whole front here is where all the digital interfaces, the CPU, and all that kind of stuff. And it is remote controllable. All the settings, they are controlled by the CPUs, relays, and electronic switches, and all that kind of stuff. I'm going to try and see if I can get in there. I didn't really plan to pull this entire front unit out, but let's see how we can get in there. So this is the time base, and there is a little add-on module here, and I believe that is for the delayed time base settings. And the time base is analog, so and it is a little bit off, by the way. Cursors and readout and all that kind of stuff, that is digital. And so there's a mismatch of the time base and the cursors at the moment. Yeah, but this is all the analog stuff, and I believe those are the trimmer capacitors. I don't want to touch any of that. We got some relays here as well. Oh yeah, here is the X amplifier. So this is, of course, the horizontal amplifier, but it's also set, so that means a brightness and blanking when it's doing the different sweeps and all that kind of stuff. And here is the deflection plates for the horizontal. We got some impedance matching stuff like that. And you can imagine a sweep here can do 1 nanosecond per division, but that is just handled by all those tiny little transistors. On the side, neatly located directly into the CRT. Let me show you. Here is, of course, the CRT, and we got some connections in here, 4 connections going directly into the CRT. So here's the vertical amplifier in one of those thick film ICs, and it's also made with cooling and all that. And if you notice something a little bit special on this scope, and that is really what I came for to find and to explain you guys, because this is very, very special. You don't see this often, but since this is an analog scope and it's going very, very fast, more than 400 megahertz, so you get input from the amplifiers via the delay line. So this is the delay line, right? And it goes into the amplifier, and this is driving the deflection plates as a transmission line pair. So there's one impedance here in one end, and then as the deflection plates gets wider and wider and more distance, impedance changes, and then you have another impedance here at the loading point, the end of the deflection plates. Then the point actually gets out again, and it is loaded at a balanced. So this is of course all balanced, push-pull and all that kind of stuff. But it's not normal. You see 4 connection points to your deflection system. Isn't that just nice? Maybe I should show you some clips from the documentation and the schematics and all that kind of stuff, so you can see the details of this fantastic deflection amplifier. So here is the bottom part. Analog inputs goes through the first stage attenuators and all that kind of stuff. It is of course controlled by the manual inputs, but those manual inputs only control the CPU, and then the CPU controls all the attenuations and stuff like that. And then we go to all the amplifiers, channel selects, chop, alternating modes and all that. And this board is called Signal Unit. It's really nicely made with impedance tracks and matched length and all that kind of stuff here for all the different signals. So have a look at that. And of course it's full of thick film integrated circuits, because it's all custom and special parts, because we want high speed here. So this is the vertical output. It goes into a balanced coax cable, and but that is not a normal coax cable. This is the delay line, and it goes all this way, and down here there's a big reel of it, and this way we can get the leading edge of a signal that we're triggering on. So that is the magic behind that. So let's look a little bit here in the CPU section and all that kind of stuff. So the first board here is the IEEE interface. And look at that, full of ICs and microcontrollers, software and all that kind of stuff. And we got cursors, microcontrollers, and all the auto setup, all the attenuator handling. Everything is done here on these boards here in the little digital section. There's even a room for another board that is not mounted, and you're not supposed to pull out the boards, and this is why everything is screwed like that. So the whole idea is you take away the front and then you pull out everything here to the front. But I don't plan to do that because everything seems to be working quite well. All those decoupling capacitors and stuff, isn't that just beautiful? Let's look a little bit here on the back. I took out both of the back units. So the one behind the CRT, that is the IEEE connector and the battery backup. And then we can see here behind the CRT, this is the on-off switch stick. Look at that. So there's a, I mean, I don't know if you can see the mechanical construction, but I just totally love it. Look at the way that this here is, of course, touching the on-off switch, and then it's bent into shape, and then there is this mechanical solution here, and then the stick goes all the way up here. Yeah, here you can see what they have done. Isn't that just cool? Because they really insist on having the on-off switch inside the power supply. So here is the power supply. I already took out the plate here that is holding the on-off switch in those two holes here. It's sitting like that. And that was, of course, missing. So a previous owner bypassed the on-off switch like that. So I guess those wires, they were just soldered to the backside of the switch. Or perhaps there was a little PCB. I really don't know. I couldn't find any documentation about the on-off switch. But what I've done is I looked in my drawers of switches and look at that one. So this is an ALPS TV-8 KD3, and if I'm not mistaken, this one will fit real easy here. All I have to do is bend these two out and then slide in the switch into the original little metal part holder here, and I believe then I have restored the switch. This is what, at least what I hope could be the solution. I will get back to that in a few seconds. So the power supply here is actually 4 different switch mode supplies. And it's because this unit has something new. There is no voltage input selector or anything like that. So this unit runs all the way from 90 to 260 volts of AC input. So input goes, of course, first to the on-off switch, and then it goes back and down to the other side. And yeah, let's look at it in the right order. AC goes into the 2 primary converters here. There are 4-watt converters, and they take in mains voltage each. There's a little rectifier here, inrush protection NTC, and they deliver 24 volts each. I do believe it's actually 25 because everywhere else it's explained as 50 volts. But maybe that is not super important how much it really is. They're not exactly the same. There's a tiny little difference between these two. So one of them also deliver a line trigger signal. So the scope can of course trigger on mains frequency. Then the 4th converter is the high voltage converter. It's also a regulated voltage converter, so it measures the output voltage and then it regulates using a comparator, so it's comparing with a Zener diode the voltage, and then it turns on and off the PWM, or the switching of the high voltage. So high voltage here, we got 2 outputs. One goes to the negative system. The cathode is on minus 3.5 kilovolt, and the anode voltage is multiplied to 21 kilovolts, and that is located here. Is the anode multiplier, and this is the 2nd stage converter. This is a flyback converter with quite a lot of outputs, and all those many outputs, they go via this thin flat cable connector here. So that will be all our outputs, 100 watts I guess of output, and this scope uses 130. So I think the 30 watts is probably what is wasted in all the power supplies, and then 100 watt is delivered to the rest of the scope. So this connector goes in here behind the CRT, and then it is distributed along this circuit board to all the different boards inside the scope. But now I'll go and play a little bit with my switch here, and hopefully I will be able to mount this correctly here. Oh, I can also show you some pictures I got from the original switch, and those pictures also explain the original switch type. So in case you got a similar scope and you want to pick up the original switch and do a repair, yeah, you could maybe do that. But I will go for this ALPS switch instead, and I believe it is very close to mechanically compatible here. So look what I did. I took the original switch holder and modified a little bit, so now it's holding my new switch. All I have to do now is solder a little bit, and it's gonna be fine, right? I really hope that this switch is going to hit the exact point of this metal rod here that will hit the switch. So it turned out quite well with this ALPS switch. First I tried to mount it the other way around so it would be easier to make the solderings and the wirings and all that kind of stuff. But it turned out that the safe distance up here is not that much, because it's touching this piece of metal here, was barely touching the solderings. So we don't want that, we want safety distance. So now I swapped it this way around, and the cut out in the aluminium here, I think this indicates that this is the way it must be mounted. So now I need to try and install it and see if it will work. There's a little challenge with those two wires here. That is of course the anode, and that will be the cathode wires, and they need to go this way around, and then they will be mounted here with this little cable holder here, and then they will come up here, so they cannot go into stuff. And then you need to do that when it is inside the unit, by the way, so it's really difficult to do. It's really difficult to assemble this, to wiggle it in and out and making sure that it goes all the way in correctly. Hold all the cables and all that kind of stuff. The anode cable and the cathode cable, I totally gave up mounting this little cable holder thing here, because it's just not making any sense. You can't move anything here, and you can't assemble this. Is, I don't know, absolutely impossible. But I got very, very good news. So remember the on-off switch. Hear this, feel this. Haha, I think this will work. So now I'm done playing with this fantastic Philips scope, and as you can see here, it is of course nicely working again. I'm super happy about this power on-off switch that is working. There's another really funny thing about this scope, and that is the CRT brightness. It is of course extremely bright, but it takes a very, very long time. Actually a few minutes after the beam is on, and then it goes more and more and more and more bright over many, many minutes. So that is funny. So if you have adjusted the brightness for a normal level, and then you just turn it off, and then next day you come and turn it on, it's just not working. Unless you wait a few minutes, then your picture comes back. That is a little bit funny that it takes that long to restore correct brightness. So anyway, that is what I wanted to show you about this really nice oscilloscope. Thank you very much for watching, and I hope to see you again soon. Bye!